Lesson 3.4 is discussing all types of rational functions. So a rational function has kind of an interesting definition. If I gave you an algebraic definition, p of x, a rational function, would be a of x over q of x, where a of x and q of x are both polynomials. So basically what you have is a division of two polynomials. And this creates some interesting attributes to a graph. We're going to see horizontal and vertical asymptotes. Sometimes we'll see X-intercepts and Y-intercepts. We also will begin to talk about oblique or slant asymptotes in this section. So they're really loaded sections. It's going to take us a few days to get through it. And there will be a calculator-free quiz coming up where I make you calculate the horizontal, vertical asymptotes, X-intercepts, Y-intercepts, all sorts of things without a calculator. So the first thing I want to talk about is the domain of a rational function. So number one, we have a numerator and denominator, and when we talk about domain, we want to think about restrictions on the x value. The only restriction that you would notice in a rational function is if you were to divide by 0. So the restriction I'm seeing is x plus 1 cannot equal 0. So a simplified version of our domain, and I'm going to let you write it in this simple notation as opposed to the interval notation, is that x cannot equal -1, indicating that everything else is fine. So same thing here on number 2. My domain restrictions would be if my denominator was equal to 0. This time we have a quadratic polynomial, so I'm going to have to factor it to see my restrictions. So my domain is that x cannot equal -3 or x cannot equal 4. The x-intercepts in a rational function can be found by setting the numerator equal to 0 and then solving. So sometimes they're very simple. 2x equals 4. So my x-intercept would be at x equals 2. We also want to be careful about something called a hole. Some of you saw holes in Algebra 2 when you were graphing rational functions, and some of you did not. So it's always a good idea, even though we're only interested in how the numerator can come out to a value of 0, you really should factor both the numerator and denominator to make sure we don't have a removable discontinuity or a hole. So my numerator in this next problem factors into x minus 3 times x plus 2, and my denominator factors into x minus 4 times x plus 3. So it would be a removable discontinuity if we were able to cancel out factor from the numerator and denominator, and since we can't do that, none of those are removable, but I'm still only interested right now in the x-intercepts. So when I set my numerator equal to 0, I get an x-intercept at 3 and another x-intercept at -2. Y-intercepts, without a calculator, the easiest way to find them is to substitute in a 0 for all the x's and then simplify, because remember, f of x is really just the y value, and when you think about a y-intercept of any graph, it's where it crosses the y-axis, and therefore the x values would be 0. So if we take this function and substitute in zeros for the x's, we get 0 minus 4, which is -4 in the numerator, and then 1 plus 0 is 1 in the denominator, so my y-intercept is at -4. Same thing for number 6. 0 minus 0 minus 6 is -6. 0 minus 0 minus 12 is -12. When I reduce that fraction, I get a 1/2 y-intercept. Vertical asymptotes. They are associated with the domain because a vertical asymptote would interrupt the domain, and if we set our denominator equal to 0 and solve, kind of similar to how we found the domain restrictions, but we also have to be careful about those removable discontinuities again. So even though we're really just interested in the denominator, we're going to have to factor the numerator as well to make sure we don't have a removable discontinuity. It causes that's what I was going to write right here. The official name is a removable discontinuity, but we refer to it as a hole because literally it is a hole through that part of the curve. So there's nothing to factor in my numerator, and my denominator is just already a linear factor. So my vertical asymptote would be at the equation, the vertical line, x equals 4. And I want you to label your components very carefully. You can abbreviate vertical asymptote VA, but make sure it is an equation of x equals 4. And again, on number 8, even though I'm not really interested in the numerator, I do need to factor just to make sure there's not a removable discontinuity. So my denominator factors into x minus 4 times x plus 2. Now, good news that we did factor everything, because we're going to see right here we have a removable discontinuity. This still would interrupt the domain, but it's not going to give me two vertical asymptotes like I originally thought I might have. I actually have a hole and one vertical asymptote. So the only vertical asymptote in this problem is at the equation of the line x equals 4. And then my next problem, whoops, I can factor an x out of the numerator, leaving me with 2x plus 3. And then my denominator, I can take a 3 out for now, x squared minus 16, but that will continue to factor further into x plus 4 and x minus 4. Now 3 is just a constant coefficient. It is not a polynomial, so it's not going to give me a vertical asymptote. But I will have two vertical asymptotes in this problem, one at x equals negative 4 and one at x equals positive 4. A horizontal asymptote is where we're going to compare the degree of the numerator and the denominator. So I'm going to give you more of a calc-like definition of what the horizontal asymptote means, and then I'm going to give you some cute sayings to remember what they are. So if we look at the degree of the numerator versus the degree of the denominator, and I want to ask you about horizontal asymptotes, what I'm asking you about truly are the left and right and behaviors. In other words, what would happen, where would the function flatten out if you were to put in either really, really large values, 1 million, 2 million, infinity, approaching infinity, or really, really small values, so negative 1 million, negative 2 million, negative infinity. And it's difficult to literally plug in a negative infinity, but what you can think about when I look at number 10 is if I were to put in, let's say, an infinity for all my x's, I would have, let's go with 1 million. 2 times 1 million squared plus 3 times 1 million. Now, even though 1 million is a huge number, 1 million squared is far bigger because you would take the 6 zeros that 1 million has and you would double them into 12 zeros. I don't even know what that number is. So essentially, when you plug in 1 million, I have a quadratic term and a linear term. This linear term, even though I'm plugging in 1 million for it, is negligible. It's not going to affect my balance of my ratio because he's so tiny in comparison to the first term. And then same thing in my denominator. The negative 48 means absolutely nothing to me. So what I'm really just interested in looking at is when I plug in really large numbers into just the lead terms of my polynomials. So the x squared would end up removing each other, cancel each other out, and I'd just be left with 2/3. And notice at the beginning of my function, f of x, we know is really a y. So my horizontal asymptote is at the equation y equals 2/3, a horizontal line at 2/3. Now, if that is not something you want to think about, then I want you to use these little sayings: top heavy, bottom heavy, and equal weight. So when I'm asking you whether this fraction is top heavy, bottom heavy, or equal weight, I'm asking you to look at the degree of the polynomial of the numerator and the denominator and compare them. So if it's top heavy, the degree of the numerator is greater than the degree of the denominator. And when you have a top heavy rational function, there is no horizontal asymptote. When you have a bottom heavy fraction, the degree of the numerator is less than the degree of the denominator. And when that happens, you will see that your horizontal asymptote will always come out to the asymptote line of y equals 0. And when you have an equal weight is where your degree of your numerator equals the degree of the denominator. That'll be like the case that we just saw in number 10. Your horizontal asymptote is going to be at y equals, and then the ratio of your coefficients. I'm going to call that z over a. The coefficients are going to be numbers, of course. So number 10, we already went through the example of doing it by thinking of substituting in really large numbers, but let's think about whether it's top heavy, bottom heavy, or equal weight. So we have a quadratic over a quadratic, which means it's equal weight. And when I follow the instructions, it says just look at your lead term coefficients. So my horizontal asymptote will be at the line y equals 2/3. Number 11, I have a linear over a quartic, which means we are bottom heavy. And the bottom heavy says when you have a bottom heavy rational expression, your horizontal asymptote is at the line y equals 0. Which means on the ends, right and left ends, it's going to be approaching the x-axis. We'll see examples of this on the calculator in a bit. And then number 12, I have a cubic over a quadratic, so we have a top-heavy fraction. And when I look at the sayings at the top, a top-heavy has no horizontal asymptote. The reason it has no horizontal asymptote is because we are actually going to have an oblique or a slant asymptote, and that is one of the next things we're going to talk about. So oblique is the fancier term, but a slant asymptote means that it's not a vertical line, it's not a horizontal line, it's a diagonal line asymptote. And that's because, if I go back to the previous example, when you have a top-heavy fraction, and I start plugging in really, really large numbers, I just keep plugging in larger and larger and larger numbers into my numerator, my denominator becomes negligible, and my function increases and then eventually decreases without bound. So we're going to end up approaching a slant asymptote. In order to find the slant asymptote, you actually have to reduce this polynomial expression through long division. And remember, a rational function is just simply a division problem. So we are going to do the division. X to the third power divided by the quantity x squared plus 4. So long division, x to the third divided by x squared is x. Make sure you multiply him by the remaining part. And then this is a pretty short problem because third step is to subtract. The first term should always cancel in long division, and I have a negative 4x, but notice negative 4x cannot be divided by the divisor of x squared. So this is actually my answer right here. The quotient, ignoring any remainder, is the equation of your slant or your oblique asymptote. So this particular function would have an oblique asymptote at y equals x. If I go to my calculator and I type in my original function into y1, let's see, and then make sure you use parentheses around your denominator. I'm also going to do something interesting. I'm going to put what I think is the oblique asymptotes equation into y2. So I'm in the standard window right now. It's a little difficult to tell. I wish I had a color screen on this. The second line that was graphed was my asymptote line. Now it's not actually a line. I just wanted to graph it for visual purposes. Do notice that as I look far to the left and far to the right on the end behaviors, the function is approaching those values. If I were to zoom out a little bit, out of the standard window, you might be able to see it a little easier, or not. Noble idea. Okay, number 14. Let's try doing long division so we can find the equation of the oblique asymptote, since that is a top-heavy rational expression. So 2x squared minus 3x plus 5 dividend divided by the divisor of x. 2x squared divided by x is 2x. 2x times x is 2x squared. And then of course we're going to subtract. Bring down negative 3x. Negative 3x divided by x is negative 3. And once I get to the linear part, I know what's going to happen next. I'm going to end up with a remainder after this. So when you do long division for the purpose of finding the oblique asymptote, you actually don't care about the remainder. You only care about the quotient before you hit the remainder. So the equation of my oblique asymptote is that guy, 2x minus 3. Okay, the next set of problems I'm going to have you basically find everything you can. So X-intercepts, Y-intercepts, vertical, horizontal asymptotes, if there is an oblique asymptote, and if there are any holes. Now, not every one of these functions is going to have most of these things even. We'll see an example of kind of everything today. And of course you can verify everything we do on our calculator, and when it comes to actually graphing the function by hand, I would expect you to find these without the calculator, and then use your calculator for a little bit of artistic assistance. So X-intercepts, we are supposed to find out when the numerator equals 0 for what values. Well, our numerator is just a constant 1, so it is never going to equal 0, so there are no X-intercepts. The Y-intercepts, remember, we're supposed to substitute in 0 values for the X. So let's see, 1 over 0 minus 4, so that would be a negative 1/4. You could put decimals, that's fine. Vertical asymptotes would be values that make my denominator equal 0. So if I were to think about that equation, it would be x equals 4, a vertical line. Horizontal asymptotes, I notice that we have a bottom-heavy expression because it's a constant over linear. And when I have a bottom-heavy expression, that means my horizontal asymptote is at y equals 0. Since it's not top-heavy, we will have no oblique asymptotes, and nothing was factorable or removable, so we have no holes. When I go to graph, even before I grab the calculator, I'm going to graph everything I can. So I noticed I had a vertical asymptote at x equals 4. Well, it's really difficult for me to graph on this tablet, but give me a minute. And then a y-intercept at negative 1/4 or negative 1/4, so right there. And when you go to your calculator and you carefully type in this function, by the way, on your no calculator quiz, I will not be having you rough in any sketches. I'm just going to have you identify all those different components of the graph algebraically. So we have 1 over x minus 4. I don't have the new math print, so I'm going to have to use very careful parentheses. Oops, I have that weird window still. So go to Zoom 6, standard window. And my calculator does not do an awesome job of graphing these, it does the best it can. So this is a hyperbola. It has 2 branches. And remember, we decided there were no x-intercepts, so be careful not to accidentally cross the x-axis. And then when you come up to the vertical asymptote that I do know, I want you to make sure that you show that it's hugging the vertical asymptote. And the same with the horizontal asymptote at y equals 0. Probably, if I was doing this on a test, I would have used my table to get some other good points, but I'm in a hurry. Okay, next question. X-intercept would be where my numerator would have values that make my numerator come equal to 0, so that's not too bad. X equals 0. Y-intercept, I'm going to substitute in zeros for all my x values, so that would give me a 0 over 0 plus 1, which is a 0. And then a vertical asymptote, there's nothing to factor, so I'm just going to set my denominator equal to 0 and find the vertical asymptotes equation. Horizontal asymptote, it is a equal weight, or an even weight, some people call it, fraction. So when it's equal weight, I'm supposed to look at the coefficients of the lead terms. So my horizontal asymptote is at y equals 1 over 1, which is y equals 1. Since it's equal weight, there's no oblique asymptote, and we saw earlier that there were no removable discontinuities. So for the sake of time, because I don't have that much time to record this lesson, I am going to sketch in everything I can and then just kind of fudge it. But you would go ahead to y equals, type in your function very carefully. There's my vertical asymptote at negative 1 and my horizontal asymptote at positive 1. And let's see, we had an x and a y-intercept at 0, which tells me that this function is going to intersect at the ordered pair 0, 0. And that kind of gives me enough information from my memory to know how to graph this, but again, you're going to use your calculator. So, bad graph. It is not supposed to be coming through the asymptotes on this one. I just am not graphing well. There's my 2 branches of my hyperbola. Again, use your calculator. Okay. So number 17. There is nothing that I could use to substitute into my numerator to make it come out to 0 because it's a constant, so there are no x-intercepts. And for y-intercepts, if I were to substitute in a 0 for the x, I get 9 over 0 minus 9, which is a value of -1. Vertical asymptote, I notice that this denominator is factorable. So I have two vertical asymptotes, one at x equals 3 and one at x equals -3. My original rational expression is bottom heavy, so my horizontal asymptote is at y equals 0. There's going to be no oblique asymptote since it's not top heavy, and there was nothing to factor and remove, so there are no holes. So again, I'm going to kind of fudge this. Ugh. Since you are not drawing on a tablet, your graphs need to look a lot better, and P.S. I would like your homework out of the book done on graph paper. I had a y-intercept at -1, no x-intercepts, and just going off my memory, I know what this looks like, but you would grab your calculator and graph it. I know, oh goodness, there's two branches on the side here. Ugh. Do not do what I did. I crossed the asymptote horribly. And then there's kind of a quadratic looking thing right here. Okay, but again, you would use your calculator, careful about the parentheses, getting all the attributes to match up to what you see on the calculator. Okay, number 18. I see a lot of factoring going on, numerator and denominator, so I'm going to go ahead and factor it through. So x plus 3, x minus 2 for the numerator, and x plus 2 and x minus 2 in the denominator. First thing I notice is there's a removable discontinuity at, if I solve that, x equals 2. Which means at the x value of 2 there's a hole, and we'll find out exactly the location of the hole in a second. But that's going to help me figure out who my vertical asymptotes are, or is. There's only one now. The x-intercept is only at -3 because of the removable discontinuity once again. And then the y-intercept, if I were to go back to the original and substitute in 0 for all my x's, I have a -6 over -4, which reduces to a 3/2 or 1.5. Sometimes when you're graphing, if it's a point or decimal is better than a fraction. Vertical asymptote, at first I thought I had 2, but because of the removable discontinuity, I realized I only have 1, and he's at x equals -2. If I go back to the original problem, I notice it was an equal weight rational expression, which means I was to look at his lead terms to find the equation for the horizontal asymptote. Well, his lead terms coefficients would be 1 over 1. So the horizontal asymptote is at y equals 1. It's not top heavy, so there's no oblique. But now let's talk about that hole. I know the x value of the hole's location is at 2. To find his other part of his ordered pair, his y value, you would do just what you think. You would substitute in 2 into the function. So, I just erased part of it. Goodness. Try again. And I'm just going to substitute it into this part of the function after removing the discontinuity, because otherwise I would get undefined values. So 2 plus 3 is 5, and then 2 plus 2 is 4, so 5/4 is an okay answer, otherwise it's decimal of 1.25. Now if you go to graph this on your calculator, you're not going to see an obvious hole. However, and let's go ahead and do this, if we tried to find that value, you wouldn't have a lot of luck. So I'm going to type in the original function with parentheses. So x squared plus x minus 6 divided by x squared minus 4. If you were to type in the updated version, like after you remove the discontinuities, you are not going to see what the original function had to offer. So you have to type in the original one. I'm in the standard window right now, and I end up with a hyperbola, And just so we're on the same page, I do seem to see an x-intercept at -3 like I thought. It does seem to have a y-intercept at 1.5. There's definitely a vertical asymptote at -2, and that is the only vertical asymptote. I see a horizontal asymptote at y = 1. There's no oblique asymptote, but hit the trace button to pull up the cursor, and then I want you to try typing an x value of 2 and see what happens. Notice it gives you an empty y = spot, and that's because of the hole that is apparently at the point 2, 1.25. If I now keep my cursor there and just go slightly to the left, see what happens to your y's, and if I go to the right, see what happens to your y's. So it's never going to find the hole graphically unless you know where to look. Even if you zoomed in really close, I don't really know a way to see it clearly. Alright, and then our last example. X-intercept. I'm going to learn my lesson from the last problem. I'm going to factor before I begin. Oh, let's see. That is not going to factor. Don't worry about that. The numerator actually doesn't factor. So we are not going to have to worry about holes on this problem, but I do notice that it's top heavy, so this must be an example where we are going to find a slant asymptote. So x-intercept, if you tried to solve this quadratic, we already saw that we couldn't factor it. If I quickly calculated the discriminant, so b squared would be 1 squared minus 4 times a times c, I'm going to notice very quickly that my discriminant is going to come out to a negative value, which means that I'm going to have imaginary solutions to that quadratic, and my x-intercepts can't be imaginary numbers, so we must have no x-intercepts. The y-intercept would be when I substitute in 0 for all the x's, and I end up with 16 over -2, which I know is a -8. Go ahead and mark that. Vertical asymptote at the line x = 2. Go ahead and mark that. Hello. And then a horizontal asymptote, I see that we have a top-heavy fraction, which means I do not have a horizontal asymptote, but however, since I have no horizontal asymptote, because of it being top-heavy, I do have an oblique. I'm going to have to do long division to find the equation of the oblique asymptote, and I'll go ahead and write down no holes. So 3x squared divided by x to the first is a 3x. Multiply him by x minus 2, and you get 3x squared minus 6x. Don't forget the third step to long division is to subtract that quantity. And 1x minus -6x is 7x. Bring down the 16. Start over. 7x divided by 1x is a +7, and I'm going to stop my work right there because I know the next step produces my remainder, which I do not care about. So the quotient is the oblique asymptotes equation line. And when you graph these, it's important that even though the oblique asymptote is not a part of the function, I want you to somehow highlight for me where the oblique asymptote is. So it starts at up 7, the line, with a y-intercept of 7. I'm going to do him in green, and then a slope of up 3, right 1. So up 3, right 1. Up 3, right 1. Careful, these boxes are counting by 2's. Up 3, right 1. So again, since he's technically an asymptote, I want you to color him in with a highlighter or a dash line of some sort, a red pen, something. And then, let's see here. We had no x-intercepts. That was the y-intercept. I filled in the asymptotes already. If you were to graph this on your calculator with an appropriate window, you would see something that kind of looks like this. So come straight down the vertical asymptote and then along the oblique asymptote over here, and something similar happens up here. Whoops. So again, use a calculator for some assistance, and you have to have a pretty big window to see both branches of this particular function. That is 3.4. Please be able to find all those components without a calculator before we take our no calculator quiz.